And I told you about the 11-dimensional supergravity multiplet with the metric and the 3 form and the Gravitino. But of course, you can also split this up into a 4-dimensional multiplet. And then you get the following multiplet. So this is based on an n equals 8 multiplet, SUSY multiplet, which has the following form. If I list the spin here and then the number of fields, so there's spin 2, that's the massless graviton. Of course, here massless. Then there are 8 gravitinos. And this you get by the standard kind of analysis. In the textbooks, you have supercharges, and you halve the number of supercharges as appropriate for massless multiplets. And then you just get 8 supercharges, and you keep applying them. And what you get is the following representations. So 28 spin 1 particles, 56 spin 1/2, and finally 70 scalars. So, and this will be represented by fields. So there will be now Vierbein. I now use these indices because we're now no longer at 11 dimensions. There will be 8 gravitinos. They will now carry an internal index that runs from 1 to 8. There will be 28 vector fields, which will be labeled like this. I will explain the reason why we use different fonts here, or different types of indices. And these spin 1/2 fermions are labeled by, well, they correspond to a tri-spinner, so they're labeled by 3 indices, and this whole thing is antisymmetric in 3 indices, and finally there are the scalars. And this is a complex field, so you can write the 70s real scalar fields as 35 scalars plus 35 pseudoscalars. And then these fields are respectively real self-dual and real anti-self-dual, so that this is complex self-dual. So this we write as 1/24 epsilon I j k L m n p q phi m n p q, where the convention is such that the indices are lowered. When you lower the indices, this corresponds to complex conjugation. There's also an SU8, and it will turn out that these indices here will be SU8 indices, so the R symmetry. The symmetry that operates on the superalgebra is SU8. And on the fermions, this will be a chiral SU8, so if the index is up, it's positive chirality, and if the index is down, it's negative chirality. There are all kinds of conventions. For example, you can also use Weil spinors, dotted and undotted spinors. Okay. So, as I said, the original intention was to construct that theory, but the main difficulty back then was that the theory is going to be non-polynomial in these scalar fields. So the technique that people had applied up for lower end supergravities, which goes by the name of Noether procedure, we simply keep adding terms and try to close the supersymmetry. In this case will not work because you will have to construct an infinite, a non-polynomial kind of action here. And this is why this was the main reason for the detour via 11 dimensions, because in 11 dimensions one has this 3-form field, and the Lagrangian, which you saw yesterday on the blackboard, is a polynomial Lagrangian, and therefore it was constructible in a finite number of steps. So, and I've already told you about this, these hidden symmetries. So the way to construct the theory was to simply take the 11-dimensional theory, perform the dimensional reduction using the kinds of decomposition I was showing yesterday, showing on the blackboard yesterday. And well, but then there's still a kind of pattern recognition, because what you get by simply taking that Lagrangian doing the dimensional reduction is something rather complicated expression, and of course there's a lot of, there are redefinitions, and what you get is not very simple. And this decisive step was indeed the recognition or the realization that this theory has this hidden symmetry. Now, one thing, when you reduce from, reduce gravity from higher dimensions to lower dimensions, then the internal part of the field line is then, so you start with this, say, Elfbein, and you split it like this, and a very convenient tool here, or a very useful tool here, is to make use of the local Lorentz symmetry to put 0 here. So this is what's called triangular gauge. And this is also something that will recur later on. And then this Vielbein has the following structure. So here you put the 4-dimensional Vielbein. You also have to include a Weil-Weiss scaling factor, but let me just skip over this. And then here you put the Kaluza-Klein vectors. There are only 7 of them. So out of these 28, you only get 7 from here. And then you put an internal Siebenbein here in this box. And this gives it basically 28 of the scalars. So it's 28 out of these 7. This is 7 out of these 28. And the remaining spin 1 and spin 0 fields will have to come from the 3-form field. Now, one thing that was known, and that's kind of obvious, is that when you simply take this kind of decomposition, substitute it into the Einstein-Hilbert action, and do the right reduction, then these scalars here will be described by a sigma model that's based on the coset space GL7 over SO7. So this is what remains of the local Lorentz invariance in 11 dimensions. So it's just a Euclidean symmetry. And the GL7 is what remains of the diffeomorphism invariance in 11 dimensions, because you've now, in this reduction, you simply drop the dependence on the internal coordinates. And then you get this symmetry enhancement by now including, first of all, so this was the EMA. Yeah?
How can you tell that the interaction is not polynomial in 4 dimensions?
You will see that it's not polynomial, because just like all sigma model actions,
So just by thinking because
pardon?
nonlinear sigma model?
Yes, it's going to be a nonlinear sigma model. I'm just trying to explain where this comes from, because I already know if I do the dimensional reduction for pure gravity and view this from a lawyer, Kaluza-Klein kind of perspective, I will of course get the Maxwell electromagnetism coupled to 4-dimensional gravity here. But here I will get a nonlinear sigma model, and this structure is inherited from the diffeomorphism invariance in the higher dimensions. So you now add to this the 7 scalars that you get by dualizing the 7 antisymmetric tensors, and thereby you increase the coset space. So you add 7 scalars, and then you can check or verify that by adding these fields you can enlarge the symmetry to SL8 over SO8. And in the final step, and that was the crucial step actually, by adding the 35 pseudoscalars A, M, and P, the theory became, the coset now becomes this coset. And as I said at the beginning, this was pure numerology, and the hard work now consisted in actually checking that this structure is really, really there. Yeah. Pardon?
Where does the metric come from?
Which metric? The four-dimensional metric. Well, that's just built from this Vierbein in the usual way.
Yeah, that's what I thought.
Yes, that's true.
Below it, you say
Oh, this is because you see, this is the Vierbein. You can choose a Lorentz gauge, and by partially exploiting the Lorentz invariance, I no longer have SO1, 10 Lorentz invariance, but I just have SO1, 3 Lorentz invariance, and here the SO7.
oh, I see. That's just a weird thing.
It's just, you see, this triangular gauge is a very important thing. As we'll also see later, it's also going to be very useful for understanding even more complicated symmetries. It's actually a crucial fact. Right? Yes? That's a good question. You see, I forgot to say this. If for n less than 8, the R symmetry is UN indeed, but for the maximal series n equals 8, it's reduced to SUN because, well, there are several places to see it, but one way to see it is that this multiplet is what's called CPT self-conjugate. You see, the way you build these multiplets is starting from a state of helicity 2. You apply the supercharges, you keep applying them, and then I haven't written the negative helicities. And normally what you have to do for lower n, so it stops somewhere, not quite at the minus the helicity at which you started, in order to make the thing CPT invariant, that's a basic requirement for quantum field theory, you have to add the CPT conjugate states. And it just turns out that for n equals 8, when you keep going, the last step here is at helicity minus 2. So this is a characteristic feature of, SU8. And you also see it here because this self-duality condition is no longer compatible with U8. This is what reduces the U8 to the SU8. It's the same thing as for n equals 4 Yang-Mills, where the group is reduced from U4 to SU4, because there as well you have, for n equals 4, you have scalar fields like this, and then you impose a self-duality constraint because you want 6 real scalar fields. So you have to impose some condition like this, where this is again the complex conjugate. And this is what breaks U4 to SU4. So whenever you have a CPT self-conjugate multiplet, then the R symmetry is reduced, and this just happens for n equals 4 Yang-Mills and for maximal n equals 8 supergravity. By the way, this may also be related to the fact that that these theories, so far at least, don't seem to admit any off-shell formulation, because when you try to formulate it in superspace, you also have to take care of this self-duality constraint when this is elevated to a superfield, and these conditions are always such that they put the theory on shell. So that's a crucial feature of this theory. You see, it's also a crucial feature for this to work, because E7 admits SU8 as a subgroup, but not U8. So that's an interesting fact. So the general pattern here that you see emerge here is that the structure here is always, of this coset, is always of the following form. Always a G, where this is some group, the group, divided by K of G, where K of G is the maximal compact subgroup of G.
It has to be like this, otherwise it wouldn't be positive.
That's correct. But you see, this is, well, but that would be a separate lecture, because this is if I do the reduction with a space-like killing vector. So all the coordinates which I drop are space-like, then it is like this. But you can also look at other kinds of solutions where you take one of the killing vectors to be time-like, which means you drop in the reduction, you drop a time coordinate, and then this becomes non-compact. Then things are more subtle. But what I'm going to do, I'm just going to drop space-like coordinates, and then it always has this kind of structure. So let me just tell you, just give you an idea what this E7 symmetry looks like, how it acts. I think I should at least show it once. Oops. Sorry. So some words about how E7 acts. So E7 is one of the exceptional groups of Killing and Cartan. So it has a 56-dimensional, so fundamental representation is 56-dimensional, and it's realized in the following way. So you write this as follows. So I take objects or 56 coordinates in this space. So these indices run from 1 to 8. This is antisymmetric. And the convention is such that this, if you pull the indices down, this is the complex conjugate of this. And then, so I just have to say how this thing, one of these things transforms. So lambda ij kl ckl plus sigma ij kl zkl. Well, these are antisymmetric pairs. And in this most general form, one sees that actually this is a matrix that is in SP56. So E7, it's an important thing to know that E7 sits inside SP56R. But in order to get E7, you have to be more specific about what these objects are. So lambda ij kl is equal to, it's actually reduced to SU8. So that's delta I k lambda j l, where this is now an SU8 generator, which means it's anti-Hermitian. And this in our notation means, anti-Hermitian means lambda equals minus lambda dagger. Dagger means complex conjugation plus transposed, and a minus sign. Sorry, like this. And furthermore, it's traceless, which implements SU8. And then the sigma is restricted to be complex self-dual. Oops, sorry. JKL MN PQ sigma MN PQ. And now you see, you can check that indeed there are 133 generators. So here we have the SU8 with 63 generators, and here we have, it's just like the 70 scalars. So here we have 70 generators. Okay, and these are compact, and these are non-compact. Pardon? This is, you see this, the restriction here, this, I don't have full antisymmetry, so I restrict this from SP56 to E7 by imposing that this should be fully antisymmetric and furthermore complex self-dual. And this, so we have 133, which is 63 compact plus 70 non-compact. And this accounts for this notation E7, 7 where the 7, so E7 is the name of the group, but this is a label for the non-compact real form, and what appears here is the number of non-compact minus compact generators. Okay, so same for E8, by the way, because there's 248, so that's for E8. You have 120 for SO16 plus 128 non-compact, so the difference is 8, so this leads towards E8. 8. There are other non-compact real forms for these algebras, they're finite in number, but in this case you choose another compact subgroup. In fact, all these real forms are realized in some one form or another in supergravity. It just so happens that in the maximal theory, it always comes in this, it's always E n n, and this is what's called the split real form. Okay, so well, there was the recognition that it was E7. Then, of course, you had to look up in the books how is E7 really realized in terms of matrices, and now we realize that that this is the realization that is appropriate to the maximal supergravity. Here we have the SU8, which is gets related to the R symmetry of the theory. And here the 7 non-compact directions are associated with the 70 scalar fields. Okay. So that now means, once I've understood how this group is realized, that this is a little bit like in general relativity. Before, people would have tried to simply parameterize the Lagrangian in terms of these 70 scalar fields. But this is like doing general relativity in some special coordinate system. And as you know, this will be a complete mess if you don't recognize the underlying structure. But once you realize it's E7, and the thing has to be compatible with this E7 sigma model structure, then everything becomes, in some sense, very easy. So it's just like in general relativity, when you write the Einstein equations, you don't write them in terms of explicit coordinates, but you first try to construct objects that behave covariantly, like the curvature and so on. And here you now do exactly the same thing. And some of this technology, of course, was already developed long before supergravity in the context of nonlinearly realized symmetries. This is work that was done already in the 60s. So, what one does now, knowing all this, we're now going to represent the scalar fields by a new kind of Vielbein, are now represented by a Vielbein, or 56-bein, if you like, V of x, which is an element of this coset space. Okay, which means that we know how the symmetries act. So all we have to do is we have to take this thing, and it transforms as follows: u of x times v of x times e to the minus 1, where u of x is the u of x is in the SU8, and e is in the E7. Okay, so this means that so this is exactly like what you get from general relativity when you look at the GL7 of a SO7 coset. There's the action of the local group from one side and of the global group from the other. So this means that this object, which originally carries 133 degrees of freedom, you can use this symmetry to remove 63, and then you're left with the 70 scalar degrees of freedom. So in particular, you can choose a special gauge, sometimes called unitary gauge. Actually, I don't know why it's called unitary gauge, but anyway, where you can now explicitly parameterize this in terms of the 70 scalars by writing something like this. Okay, so you exploit the symmetry to bring it into this form, but you can choose other gauges. By the way, another difficulty here is that would have sort of made life very difficult if you try to construct a theory in terms of these coordinates. You can also do all kinds of nonlinear field redefinitions. So these things are really like local coordinates on this E7 over SU8 manifold. And in constructing the theory, just like in general relativity, it's best to work with covariant quantities. In this sense, these phi's are not really covariant. So this is, now here you get what's called a nonlinear realization. By this is meant the following. As long as you restrict your, so the theory has now, well, to start with, it has this local SU8 and it has this global E7, which are both linearly realized. If you now choose a particular gauge, then the symmetry is reduced. And if you choose, then you can still act with global SU8, and they will just transform this thing covariantly. But if you now do transformation in E7 with regard to the remaining 70 coordinates, then what happens is that this transformation in general will destroy this gauge, and therefore you have to introduce a compensating rotation to bring the thing back to the chosen gauge. So then the E7 action of nonlinear action or realization. Yes, right. It's so the nonlinear realization then acts as follows. It goes like Ux of E times V of X times e to the minus 1. So in case it's a transformation corresponding to the 70 non-compact directions, this action will throw you out of this gauge, and then you need a compensating rotation to go back into the gauge, and thereby the whole thing becomes realized non-linearly. So you have a choice. Either you choose to work with a linear realization, keep this as a local symmetry, or otherwise choose a gauge and just simply work in terms of the physical fields, but then the E7 will be realized non-linearly. This is, by the way, if you ask about the action on the fermions, in the linear realization, the fermions will not see the E7, they will just see this SU8, and it's only when you choose a special gauge, SU8 gauge like this, that the fermions start to see and start transforming on the E7, but only via this induced compensating rotation. By the way, also in doing the reduction, I showed you the triangular gauge. There as well, you have to pay attention to such things. When you do supersymmetry transformation, you may be thrown out of this triangular gauge, and then you have to introduce compensating transformations to be. So all these things you have to keep track of very carefully. So so I'm just sort of sketching how it goes. Now, once you're given this this structure here, as I said, it's much better to work kind of covariantly, and this you do by. So let me just give you a basic flavor of construction, because once you have this, it's relatively easy to construct the Lagrangian. what was very difficult before, almost impossible, now becomes basically very easy. Basic flavor of construction, of course. So what you do, we now need to define kinetic terms. We want to see how this scalar fields couple to the fermions and so on. And I said the rule, as I said, the rule is to try to work covariantly. So you simply look at what's called the Cartan form. And this is, so you take the derivative of this V and then you multiply it by the inverse matrix. And this, as Cartan told us, or maybe it was already known by Sophus Lee, I'm not sure. This is, again, this expression is in the Lie algebra of E7. So you can decompose it like this, where this is in the SU8 Lie algebra, and this is in the orthogonal complement. Okay, now you see from this transformation, you see this has been constructed in such a way that the Q and P don't see the E7 transformation because the E7 transformation sits inside. And therefore you have the following transformation properties on the local SU8. We have Q prime is equal to U d mu plus Q mu u to the minus 1, and P mu prime is U times P mu times u to the minus 1. Okay, this you get directly from substituting this transformation law into this formula. So what we see here is that this thing acts like an SU8 connection. But this is not a fundamental gauge field. It's a composite gauge field that's made out of the scalar fields. And this thing transforms covariantly, meaning there's no derivative on the transformation parameter. Now, because it's E7, we know that the Q mu, which is, I mean, in this representation looks like this. It's really delta I k Q mu JL. And the P mu is again an antisymmetric in these four indices. And when you substitute this expansion, for example, in these coordinates, you see that this is d mu phi ij k L plus an infinite series of nonlinear terms. So what we now constructed is something like, in the first lecture, the spin connection. You know, out of the vielbein, I construct by using one derivative, inverse, and so on. I construct objects that transform covariantly under Lorentz group. And now, in this way, I've now constructed objects that transform covariantly under this SU8. So, once you have this, now it's now fairly easy to sort of work out what the Lagrangian is, because I now simply write down the things that are compatible with all these invariances, and rather than getting a mess as I would get from doing the dimensional reduction, I get basically rather simple expressions. So let's just take one example. Pardon?
Question. So the Nonlinear degrees of freedom that you get here are all in the representation of SU8?
No. This is what I wrote here. The fermions are in a complex SU8, but the SU8 acts chirally. Maybe I should have said this. Let me see. Yes, I should. There are many things that I think I should have said and I forget to say. As you go from here to here, you need an imaginary unit, because here it's real, here it becomes complex. And on the fermions, the imaginary unit is the gamma 5 matrix, which acts chirally. So while the SO8 acts vector-like, it's a vector-like symmetry on the fermions, if you go to the SU8, it acts chirally on the fermions, and the same here. Yeah, I will comment on this, because here this is a little bit special, because I'll come to this. But let me just
So is it obvious that there are no anomalies due to the fermions?
anomalies.
Yeah, SU8 anomalies.
There are no SU8 anomalies. That's actually a nice paper by Neil Marcus of 1985, where he showed, because here you have this chiral SU8, which would be UN for lower n, and he showed actually that for n equals 5, 6, and 8, the anomalies cancel. This is a rather tricky thing, because in order to cancel the anomaly, I need to tell something about the vectors, because the vectors are also kind of, you need the vectors to cancel the anomaly. It's a little bit like type 2b. In type 2b, you also have an anomaly, you think you have one, and the anomaly cancels because there's this self-dual 5-form field strength. So it's very similar to this, but that's just a side remark. Yes? The involution that defines the symmetric space. Yes, it's just it's just Hermitian, anti-Hermitian. So the structure of the Lie algebra is, I haven't written it, is on the diagonal you have these anti-Hermitian generators, and the off diagonal with the phi's, it's Hermitian. Yes. I will do this a little more systematically once we get to E10. So, as I said, with this, given this, the nonlinear structure has sort of been packaged and, made manageable by going to this kind of covariant formalism. So, for example, if we now look at the Gravitational transformation rule, we can more or less write it down immediately. Well, not quite, but almost. Just in all supergravity theories, we have the Lorentz covariant derivative. So this is just the spin connection. But now, because we insist on SU8 covariance, the only thing that can happen here is that the derivative here must be, because we insist on local SU8 invariance, that this must couple with a covariant derivative with the spinors, and then there are also other terms, because I also have the contribution from the spin 1, and I also have cubic contributions in the fermions, but this is basically the structure. So what was before a horrible nonlinear expression in terms of the scalar fields now becomes very simple, because I've isolated via this trick here, I've isolated an object that transforms properly as an SU8 connection, and this way you can see that the SU8 is realized as a local symmetry. If you want, you can make this slightly more explicit in terms of where it came from in 11 dimensions. If I analyze what this is in terms of the original 11-dimensional fields, I will have the following components. I will have omega mu AB, gamma AB, where these are 7-dimensional indices, and the gamma A just come from the SO7 Clifford algebra. So this is what I would get by direct dimensional reduction. And now I have to add to this roughly, I mean, I'm not fixing coefficients and not worrying about such things. Epsilon u nu rho sigma f nu rho sigma a gamma a plus, and then here I need a gamma 5, roughly speaking, f abc gamma abc. And it turns out this is in agreement with the fact that if I take the SO7 Clifford algebra that's generated by 7 gamma matrices, SO7 gamma matrices, then this combination generates the SO7 itself. So I can now you can now check that if you take this with this, it generates an SO8 rather than SO7. And then, using also this gamma matrix, I can show that this whole set of matrices closes into the Lie algebra of SU8. And this is already an example where you see in the original 11-dimensional theory, if you remember, we had something like omega at delta psi m dm of the 11-dimensional omega epsilon, and then we had terms with f epsilon. And here you see what appeared like, you know, a very peculiar combination of field strengths, and here have the spin connection. It now, as you view it from lower dimensions, it turns out that all these expressions here combine properly to make this into an SU8 covariant expression. So, of course, now at this point you still have to work quite hard in order to get the Lagrangian, but at least you now have somehow tamed the non-polynomial structure of this Lagrangian. And let me repeat, just like in general relativity, the recipe is to always work with covariant objects. Don't work in local coordinates. So, and similarly, you will, for example, when you look at the variation of this field, you will find expressions, since it has to be covariant with respect to SU8, it will look like something like this plus other terms, where here again you have the nonlinear structure. And the kinetic term, just like in any kind of sigma model, is just the square of this, and then you know it will respect all the invariances. Yes, okay. Now for the vectors, because this is a bit tricky, because here you don't, I mean, here it's clear how to make this into an SU8 fermion by making it chiral, because thinking of the gamma 5 as a kind of imaginary unit. We've also seen how to make this, to complexify this or understand in what way it is an SU8 representation. But here, the question, what is this? Because here we're left with 28, or we're given 28 real vector fields. Now, real 28 is not a representation of SU8, so I have to somehow complexify it. And the way this happens is, and I just want to give you a very simple example how to do this, because now we have to introduce the dual magnetic potentials in order to make the symmetry fully apparent. And this is, you know, I'll just show you how this works in the case of, first show you how this works in the case of Maxwell theory, because, let me see, I have this right. So this is a funny way to do Maxwell theory. Theory again, just to see how this works. You can formulate Maxwell theory. Maxwell theory is normally formulated in terms of just one vector potential, mu. But now let me introduce another potential, or add to it a dual magnetic potential. Okay. And then we define the complex combination A mu, which is A mu 1 plus I A mu 2. Okay. Okay, and I form field strengths in the same way, just in the usual way. Okay, so now I have a complex field strength in which I see exactly or can realize explicitly the electromagnetic U1 duality rotations that rotate electric into magnetic fields. You know the Maxwell equations in empty space are invariant under such complex rotations of the electric into the magnetic field. And then we simply define the following combinations: anti-self dual and so this is 1/2 f mu nu plus, and now it's important, I over 2 epsilon mu nu rho sigma f rho sigma plus minus. Okay, so this is complex self-dual, anti-self-dual. Why did I put the I here? The I put here because in 4 dimensions with signature 1, 3, the epsilon squares to -1. So this is why if you want to do instantons, you have to go to Euclidean, because only there the epsilon squares to +1, here it squares to -1. In order to fix this, I put an I here. And then you can easily check that the Maximal equations follow equations from simply imposing the requirement that this be equal to 0. That's one way it's a funny way to write Maxwell theory. But what this does, it sort of equates or tells us that the field strength of this one is dual to the field strength of this one, and thereby, by the Bianchi, we are forced on shell. So what you do here with the vectors is exactly the same, and except that, of course, we have to worry about the scalar field dependence. So what do we do? No, not really. I mean, this is just a formal device. Here, I won't tell you anything about instantons. I'm just trying to exhibit the fact how the E7 really becomes realized, and thereby also the SU8, on the vector field. And as I said, just like here, in order to make this U1 electromagnetic symmetry manifest, you have to introduce the dual potential in this particular way, and then you impose this condition in order to put the theory on shell and to eliminate. I mean, it looks like you double the number of degrees of freedom, but you halve them again by this condition. Now here you do exactly the same, more or less. So you have field strength associated with this with these 28 vector fields, and then you also have G mu nu. The dual ones on shell are defined as modulo vierbein determinant factors as dl by delta f mu nu ij, and then dual, okay, or star. Anyway, sometimes I use this for the epsilon, sometimes I use star with differential forms. And then you see that you can combine the Bianchis and equations of motion by simply requiring the Bianchi on these 56 objects. Because then here it becomes the divergence if you remove this, and then this is just the equation of motion. So this thing in Maxwell theory is of course nothing but f mu nu itself, but because in this theory is of course much more complicated, this will have scalar modifications and will have Fermi bilinears and so on, but this is basically what it is. So now what you do, you now take this f mu nu m and put this into 56 component vector f mu nu ij, g mu nu ij. Okay, and then you declare this to be an object that transforms under E7. Okay, Now at this point it's still real. I didn't tell you that E7 also admits not only SU8 as a subgroup but also SL8. This is a little bit subtle, would actually require more time to explain, but so you just have to take it as I tell you. And then the whole equations of motion for this vector field can be made E7 covariant. So I simply have to write something analogous to this constraint, but now make it compatible with E7. And the way I do this is I notice that this being an E7 index, I can use this scalar field bind to convert E7 indices into SU8 indices by means of this 56 spine. So I look at this object, so I apply this matrix, the matrix V is 56 by 56. I can apply it to this, call it F. So roughly speaking, it's like this. And then I simply also need an imaginary unit, the I. And the I here gets replaced by the symplectic metric. I told you that E7 sits inside SP56, therefore there's a symplectic thing. And then I simply write something like this. And here you see we're also using this knowledge from general relativity that you can freely convert between flat and curved indices. So I think of this like a curved index. I use this 56 spine to flatten the index, and then I get a very simple relation. And this is what sometimes called twisted self-duality constraint. And in this way, I've now, by doubling, just like here, I've complexified. I've been able, in this way, to realize a complex U1 rotation symmetry on something where I only had a real field to start with. By doubling it and posing the constraint, I have exactly the same mechanism in n equals 8 supergravity. So, of course, if you look at it in detail, it's much more complicated. Well, it's slightly more complicated than this, but anyway. So, so much because I just said I wanted to give you a flavor. If you want to work it out in detail, of course, you have to do a lot of calculations, which I have no time and would not take much too long. But in this way, building up the Lagrangian, building up the transformation rules, you can ensure that the theory is fully compatible with this E7 and SU8 symmetry structure. And let me repeat, without knowing these symmetries, it's basically an impossible task to construct the Lagrangian. Once you know the symmetry structure, it's, well, quote unquote, easy, although there's still a lot of work.
Makes it manifest that you'll never find off-shell.
Well, that's, actually the answer is not known, but the fact that people have tried for 35 years to find off-shell, same with n equals 4 Yang-Mills, and it seems to be, I mean, there are even people claiming no-go theorems, but it seems...
In the n equals 4 Yang-Mills case, you don't have to introduce the extra realization of self-duality.
Yes, right. Anyway, that's one of the problems with this theory, and also one of the problems in deciding, how to do higher order corrections.
So sorry about this off-shell question. The nodal theorems always assume finite many auxiliary fields?
Yes, sure. Yes, of course. That's what people tried, but even with infinitely many fields. And I remember a long time ago I was doing superstring, at least in the beginning, I was involved in the superstring field theory program. And the hope was that this way, by introducing infinitely many fields, one would find an off-shell formalism, but no.
But there is the pure spinor superspace. Sedawall wrote down a...
Well, that's a different... No, here by off-shell I simply mean that you add fields to this theory, auxiliary fields of some kind, in such a way that everything closes off shell.
Yeah, but that's what pure symmetry superspace does. It's like a general extension of harmonic superspace.
Well, there's also harmonic superspace, but harmonic superspace, there you have an infinite number of auxiliary fields, but that only goes up to, I think, n equals 3 for supersymmetric animals. There is no manifestly n equals 4 supersymmetric off-shell formulation of n equals 4 super-Yang-Mills theory. So I thought at this point, because it's certainly of some interest, to give you sort of just an update on the finiteness, or simply make a table so you can see where we are with this. Let me see. So, finiteness or not. And in this subject, you know, there was a long time ago, at least 30 years ago, when we were working on this, I thought this is basically hopeless. There were, of course, all kinds of superspace arguments, but on-shell superspace, I should say, so they're not too conclusive. But it looked like it was basically an impossible task to do this. But as you know, very recently people, or not so recently, people have been able, in particular Sri Byrne, Lance Dixon, Radu Royban, Hendrik Johansson, and may have forgotten a few names, have developed techniques that are truly amazing from my point of view, because in fact, you know, Sri Byrne told me that he never ever looked at the Lagrangian of n equals 8 supergravity. He simply ignored it. And because if you do it the conventional Feynman way, it's by the time they're now doing 5 loops, it's been said that there are more Feynman diagrams than our brain cells in your brain. So here's a sort of where we are in this. So let me here write the number of loops. So here also. So then we have, we just put pure Einstein. So that's n equals 0. And then we have n equals, well, 1, 2, 3, say. Well, I'm doing this a little globally. There's n equals 4. N equals 4. There's now results on n equals 5. N equals 5. And finally n equals 8. Okay. So pure Einstein. So 1, 2, 3, 5, 6, 7. So it's 1, 2, and so on. Now for pure Einstein, the first calculation was done by Toft and Feldman already in 1974 or so. And what they found is a divergence, but they also realized that this divergence could be absorbed into an infinite redefinition of the metric, or metric fluctuation, and therefore it was, so circle means it's okay, so it's one loop finite. This finiteness is lost if you couple pure Einstein to matter. But then in early 80s there was this famous calculation by Gorov, Sanyotti, and later Anton van der Ven, who showed actually that the counter term, two-loop counter term, which goes like, well, counter terms go roughly like Riemann to the power loop plus 1. So here appears a two-loop counter term, which is third order in the Riemann tensor with a non-vanishing coefficient. And then, although no one will ever check this, but you can be sure that this is divergent. So this just confirms that pure gravity is a non-renormalizable theory in 4 dimensions. For n equals 1, there's actually no real calculation so far, other than what you imply from the calculations that are being done up here. But the first argument was that you try to make this supersymmetric, and it was shown you that this particular counterterm does not admit a supersymmetric extension, and therefore it is believed that these theories are finite up to 2 loops. But it was shown that there's a 3-loop counterterm. There's an expression involving this so-called Bell-Robinson tensor, which is a 4th order in the Riemann tensor, and that can be made supersymmetric. So the theory is suspected of being divergent from 3 loops on. But this is, in some sense, still undecided. Okay. Now, these techniques that Byrne et al. Have developed are of an entirely different form. They use, much inspiration from string theory. I will not. For one thing, I'm not a specialist on this, but they certainly have found a way to circumvent or to get rid of this baggage that comes with the conventional Feynman diagram formalism, which, by the way, is due to the fact that once you have all these symmetries, then you need ghosts and maybe even ghosts for ghosts, and then the life becomes very complicated, and they just calculate with onshore quantities or degrees of freedom. So n equals 4 is being shown to be finite up to 3 loops, and this was an actual calculation. So let me put this was done in a paper 1202-3923. So they've done this. And more recently, they've shown that actually that there does appear divergence at 4 loops. This was only about a year ago. 498. And therefore, we now think that these theories are divergent. In fact, this was actually the first time an actual divergence of a 4-dimensional supergravity was exhibited explicitly. You see, this discussion has been going on. People have been talking about, in particular, Anton van der Ven wanted to generalize this to do the 3-loop, but it finally wasn't done. So this is the first time there's actually a divergence in a supergravity theory. More recently, they've also done n equals 5, and now it turns out that this is also finite at 4 loops. So this was also done, but here we don't know. Okay, finally n equals 8, and this is what they started out doing. So these calculations were explicitly done, establishing finiteness up to 4 loops, and this was done in 2009. And now maybe you've heard that this is still 4, so maybe 5 goes up here. So this is what they're now doing, and they've been trying this for the last 2 years or so. It appears that they're stuck, but the conjecture is that the theory is finite also at 5, 6 loops, and at 7 loops there may appear a divergence. Now, why are they doing 5 loops if everyone expects the theory to be finite? The reason is that they want to test what they want to test. Why 5 loops? Well, there are 2 sort of conjectured formulas for the onset of divergences in supergravity. One is the following. So this is, well, let me put this D critical. This is the formula, this is number of loops, and this is in dimensional regularization where you expect a first divergence to appear. And the way they do the calculation is that they use dimensional regularization, so you can really see at which dimension the divergence begin. So it's number 1, and this is number 2. And this was a very old conjectured formula from many years ago. These formulas are not proven. They're always based on some kind of assumed or probably even non-existent superspace formulation of the theory. So you should not be too... you should not trust these formulas too much, except to say that this is the formula that is valid for super Yang-Mills. Okay, so this is the Susy Yang-Mills formula. And one thing they have shown up to 4 loops, up to here at least, they've shown that actually divergence behavior of n equals 8 supergravity is exactly like n equals 4. So it's more than just that it's finite, but up to and including 4 loops, it behaves exactly like n equals 4 Yang-Mills. This formula, which is a very old conjectured formula, this would tell you that so here you will not see any divergences at any loops in 4 dimensions, but you can check that in 5, 6, 7, where you get the divergences are exactly in agreement with this formula. This is the formula that when you put L equal to 7, you see that this becomes equal to 4, and this was a naive expectation that a divergence should appear at 7 loops. So the test at 5 loops is to see where the divergence is. So is it at 26 over 5, or, and here you get 24 over 5. So that's the only question they want to answer by this calculation. After doing all these diagrams, is the divergence, is it in this dimension or is it in this dimension?
Sorry, where did the second conjecture come from?
Well, as I said, this is old. This formula, I think the first person to put this forward was Warren Siegel many, many years ago. And I cannot, I would have to look up the argument. But usually these arguments somehow assume that there's some off-shelf formulation of the theory.
I thought the first conjecture at least had a robust argument based on the unit vector cut.
Yes, right. Yes, correct. Anyway, so this is what's now under scrutiny, and well, I was hoping that we would already know earlier last year, but apparently they're stuck at the moment.
But why do you have to go to L equals to 5 to compare these two formulas?
No, because what they've shown up to 4 loops, it's this formula, not this one.
So you already ruled this one out?
No. No, because you see, if you could show that this was the correct formula, then you would have shown finiteness, because then it would be exactly like Yang-Mills. Well, I'm kind of, I mean, my lecture here is more on symmetry. It's not on how to do helicity, amplitudes, and such things. So in the old days, the way this was done was that one had a superspace formalism, but the superspace formalism was on-shell. So you introduce superspace constraints in n equals 8 superspace, and then you simply look for quantities that do not vanish on shell. And this counter term at 7 loop, this was the first one that sort of appeared naturally. This was just what's called the superspace volume, well, E, where you here take the superspace Vielbein superdetermined, the Berezinian, and here this is much more complicated than it looks, because in order to evaluate this you have to use the constraints, and then you would have to expand in superspace coordinates to actually exhibit this structure, which is r to the 8th or d to the 8th, r to the 4th, whatever. But this is no one has ever done. Anyway, very recently it was shown by Kelly Stell, Guillaume Bossard, Pierre Van Hove, and Paul Howe, actually that the superspace volume vanishes for all n. There's some likelihood that actually this thing is not there. And in fact, they've also recently exhibited examples of finiteness. I think this n equals 5 one is a case in point, where there's no argument that would forbid the appearance of this divergence of this counter term. This is what they refer to as enhanced cancellations. So let me just conclude by saying, what can we say from the point of view of E7? Of course, one has to argue that E7 and full supersymmetry is valid in perturbation theory. We have some evidence for that. So any counter term would have to be compatible with these symmetries. Now in superspace, of course, this is manifestly supersymmetric. It also looked like at the time it was E7 symmetric, but there's a problem here, and it also has to do with this formula here, because this formula is valid at tree level. If you add corrections, this formula will also be corrected. And what actually happens, and this is explained in the paper I wrote with Guillaume Bossard, which carries the title Counterterms versus Dualities, you can sort of deform this. You can go from here to what we call a deformed, twisted self-duality constraint by introducing here a functional which is manifestly duality invariant, and then again imposing this constraint. But when then you try to solve this constraint, actually it turns out that this is not enough, but what you need is an infinite string of higher order interactions. And this is what Renata Carlos, she has referred to this as Born-Infeld n equals 8 supergravity. It means that, if you just have an r to the 8th, say, counter term, in order to really make it E7 compatible with E7, you would have to add an infinite string of higher order corrections. So the truth of the matter, I think, is from this point of view, at this point there's no counter term known that would satisfy the full nonlinear E7 and at the same time the full nonlinear n equals 8 supersymmetry.
So the fact that you have to add an even number doesn't...
No, we have, what we showed here is that actually you can do this in a simple example. You can actually work out what it is. You can make it compatible, just like Born-Infeld theory. When you expand it, it's an infinite series, but it's still duality invariant. But then the question is, once you do this, you have to, of course, also make it compatible with supersymmetry again. And in fact, I think Renata tried to do this in a superspace formalism, and it looks like it cannot be done. So I just want to say this because this issue, from this point of view, is a good deal more complicated than one might think, and therefore these calculations are certainly valuable calculations. So
this point about supergravity for is it starting at r to the 8? Did you say?
That's that. Yeah, right.
So like r to the 4th is not compatible with E7.
Well, this counter term would be either r to the 8th, or you replace two derivatives by. So, the concrete structure of this thing, when you really want to write it out, is impossibly difficult. So, anyway, so this is just where we are. This issue is still open.
But
So-
Hermann, imagine, okay, I don't know if in our lifetime we will
No,
solve
probably-
that issue. But imagine that n equal 8 supergravity, perturbatively at least, doesn't need the UV completion. So how would that theory work? What does it predict about nature? What kind of theory is this?
There's a question of what you want the theory to predict. One thing, it should predict the low energy particle spectrum that we see, but at the same time, and this is why, even if it's finite, this will not be the end of the story. It may not even be the final answer, because we still need to understand quantum gravity in the sense that, perturbative, but there are all kinds of let's this will be my last lecture.
So sorry, can you just comment on the point about supergravity? I think from the point of view of scattering amplitudes, one expects that the E7 constraints would be realized as self-finite theorems. And if you add a very high derivative term, say at for a 4-point amplitude with many derivatives, then it tends to be that you can always obey the self-finite theorems.
Yes,
so
that's
it's not
this.
surprising that with enough number of derivatives, you can be compatible with E7 constraints. So you think that if you have no number of derivatives, you can maybe always complete that.
Anyway, I wanted to spend the last. We'll leave the discussion of what this could mean for quantum gravity to a glass of over a glass of wine. Okay. So where's the? So the last thing I wanted to say is about 4 dimensions. Is of course that the theories are not unique, but you can also deform them by gauging. And this is just to give you again, just to give you a flavor of what this is. I told you that n equals 8 was obtained by reduction on T7, which simply means dropping all the coordinates, and then you get this Cramér-Julia theory. But of course, you can also compactify on other things like Kaluza-Klein compactification on, say, S7. This would give SOH gauged supergravity. Supergravity. But you can also do other things like Scherk-Schwarz, which is Schwarz with or without flux, without flux. In all cases, you get what's called gauged supergravities. And gauged supergravities means that, you see, in this original n equals 8 theory, there's just a U1. You have 28 abelian vector fields. But you can now try to couple these, introduce minimal couplings of these vector fields to the other fields of the theory. And this is what's called gauging. Replace d mu by some kind of covariant derivative where you replace the derivatives by covariant derivatives with respect to these vector fields. Now, to start with, of course, what we gauge here is a subgroup of E7. So we write this as follows, and I'm just going to give you, as I said, a flavor of this. So originally, one just took the 28 vector fields here and then took some 28 parameter subgroup of E7. So originally it was SO8, but later on people realized it could also be done with non-compact gauge groups and non-semis, or even more general gauge groups. But the most general way to do this is as follows. We take all 56 vector fields, which seems kind of strange, but and we simply take an object here, and here we put. So here we put because we know that the gauge group is going to be a subgroup of E7. So let's put all the E7 generators here. Then put something here which is now called the embedding tensor. And then we sum over all 56 vector fields. So what will happen is that out of these 56 vector fields, only 28 will actually appear. How they appear is encoded into this embedding tensor. And this possibility is, I mean, you would think, why not just stick with the original 28 vector fields? But in some sense, the theory makes use of the possibility that either just takes the original electric 28 vectors, but there also appear gaugings which can be interpreted, where the gauge fields are interpreted as coming partly from the electrical, partly from the magnetic sector. And such examples you can actually construct very explicitly for Schurk-Schwarz gaugings. This is something, last year I wrote a paper with Hadi and Marty Godaskar where this is explained in all detail, where you can see which gauge fields that appear are electric or magnetic. So the formalism to deal with this comes here. And the most general way to deal with these gaugings is in terms of this embedding tensor. Now, this is the main result here. If you look at this object, here we have the 56 indices, so this is a 56 of E7, and this is in the adjoint of E7, so theta is in the 56, the product of the 56 with the 133. So when you look at the table and work out what this is, you find the following, 640. So these are representations of E7, and you have a consistent gauging if theta is in the 912. And I'm mentioning this because in my last lecture I showed you that if you look at the tensors, not just at the spin 1, spin 0 fields, but also 2-form fields, 3-form fields, then strange new representations of E7 start to appear. And it just so happens that this 912 representation appears here because it sort of encapsulates all the kinds of deformations you can make of the theory that effectively boil down to gauging of the theory. And this has now been developed and studied in quite some detail. Well, the original paper is the one I wrote with Henning Samtleben, but more recently, or after that, it was analyzed by Bernard de Witt and Mario Trigiante and Henning Samtleben. So all this formalism has now been developed, and we now also understand how this works in other dimensions. And the lesson here is that in order to understand the deformed maximal supergravities that you get either by gauging or by doing non-trivial compactifications, all this information is contained in an object which transforms as a non-obvious representation of E7. Yeah. So this was just to...
Sorry?
Yes?
Do we know, for instance, that there are stable vacuum in the gauge supergravity?
Oh, yeah, that's another point I forgot to mention. The original theory here, because of this E7 invariance and this sigma model structure, only has derivative couplings. They all appear via this thing which I called P mu, IJKL, which starts out as derivative, and then you have an infinite string of higher order terms, but always with derivatives. So in that formulation, theory has no potential. There's an infinite degeneracy. You can put your vacuum wherever you like. This is, of course, just the homogeneous space E7 over SU8. When you gauge, you get a potential. You also get potential plus Yukawa type interactions, which were not there before. And then, of course, the degeneracy, vacuum degeneracy is broken. And then you get, you can investigate the stationary structure of the potential, and then it turns out there are quite a few stationary points. Actually, this was something that was done in the early 80s, first by Nick Warner. That was his PhD thesis. Actually, the problem was, it was given by Stephen Hawking. So he classified well, you have to do this in a 7-dimensional space of scalar fields, which is not so obvious. He classified all the stationary points that leave intact at least an SU3 symmetry at the stationary point. He found 6 stationary points. More recently, with all this technology, there's now an encyclopedic dictionary of stationary points, and that was done by my former PhD student Thomas Fischbacher. He does this with a computer, and by now they're on the order of 50 stationary points. And they're all ADS, of course. So they're ADS. Some of them are supersymmetric, but most of them are non-supersymmetric, and most of them are unstable in the Breitenlohner-Friedmann sense. There are only very few ones that are stable. The supersymmetric ones are all stable, but among all those, there's only a single one that breaks the supersymmetry, is nevertheless stable in this Breitenlohner-Friedmann sense. No, I haven't discussed alpha prime corrections here. No, this is still the tree-level theory. Yes, that's been that's work over many years. This has now been completely established that this is a consistent truncation. You see, maybe I should also say this, because what you do, many people are not aware of this, and I think it's a highly relevant issue also for people looking at, say, Calabi-Yau compactifications, but because what they do, very often you take your Calabi-Yau, you go down, and then at some point you have to, guess what is the superpotential. Then you look for stationary points of the superpotential or for the potential. But then there's a question, does this really correspond to a solution of the higher dimensional theory? And consistent truncation means that every solution of the lower dimensional theory, every stationary point, or even more complicated solutions, should have a corresponding solution that can be lifted to higher dimensions. And in Kaluza-Klein theory, many truncations are just not consistent, or in the sense that you cannot show that they're consistent. But here, because of the high degree of symmetry, this problem has been completely solved.